The earliest recorded idea of infinity comes from the Greek philosopher Anaximander. However, the first clear account of infinity comes from Zeno of Elea, another Greek philosopher. He came up with a paradox in which he is walking to the park. However, to get to the park, he first has to walk half the distance, then half the distance again, and again, an infinite number of times. So does he ever get to the park? And if so, how long does it take? Well, if we say that Zeno is walking at 1 mile per hour, and the park is 1 mile away, using time equals distance divided by speed, we can work out that the time should take 1 hour. The way mathematicians answer this paradox is as follows. The first half of the journey will take half an hour, using the same equation, and the half the remaining distance will take a quarter of an hour, and the half the remaining distance will take an eighth, and so on. So, if we put this into equation, we get time, t, equals a half plus a quarter plus an eighth, and so on. We can then half t to get a quarter plus an eighth plus a 16th, and so on. Now we see that each term pairs with the one above it, so if we minus half t, we get half t equals a half, because we minus a quarter and an eighth and a 16th, and so on. So we can times this equation by 2 to get t equals 1. So it takes 1 hour for Zeno to get to the park. The key to this paradox is the fact that the times are getting smaller, so we can add an infinite number of numbers and get a finite number as long as the numbers are getting smaller. So if we had a set amount of cookie dough, we can make an infinite amount of cookies from it by taking half the dough, then a quarter, then an eighth, and so on. However, eventually the cookies will be so small we won't be able to see them. However, some sequences of infinite number of numbers that get smaller aren't finite. Take the Harmonics Series. This is a series that goes a half, a third, a quarter, a fifth, and so on. We can prove that the terms of this series don't add up to a finite number by putting the series in clumps. Our first clump could be just 1/2, so that clump adds to 1/2. Our second could be up to 1/4. So we know that our second clump must add to more than a half, because a quarter plus a quarter is a half, and a third is bigger than a quarter. Our next clump could be up to an eighth, and this clump must add to more than a half as well, because 4 times 1/8 is a half, and a fifth and a sixth and a seventh are bigger than 1/8. So we can carry this on forever until we get to an infinite number of halves, which must add up to an infinite number. So the key to an infinite number of numbers adding up to a finite number is that the numbers must get smaller quickly enough. Therefore, if we had cookies with the radiuses of the Harmonics series laid out in a line, the line will go on forever. However, we can make these cookies from a finite amount of dough. Here's how. For the nth cookie in this series, the radius would be 1/m. The volume of these cookies will then be pi r squared times the height of the cookie, so the nth cookie would have a volume of pi times h over n squared, which gives us a sequence as follows. However, the pi h stays the same, so let's ignore this for now and get to the sequence of 1/n squared. Mathematicians have proven that the area under the graph of 1/x squared after 1 has a finite sum, and if we plot the sequence we had of 1/n on the same graph, we get this. So, as our bars take less area than the area under the graph, the sequence adds to a finite number. So, to get our original sequence of pi times h over n squared, we would just times the whole sequence by pi h, which is finite. This must result in a finite number, because finite number times a finite number is always finite. So even though, laid out, the cookies would make an infinitely long line, their volumes would add to a finite number, and so we can make them out of a finite amount of dough. Another, simpler paradox is called the dartsboard paradox, in which we throw a dart at a dartsboard. Let's imagine that we will definitely hit the dartsboard, so the probability of hitting the dartsboard is 1. However, what is the probability that the exact centre of my dart will hit this exact spot on my dartsboard? Well, there is an infinite number of points on a dartsboard, because we can always take 2 points and make a new point in the middle of them. If the probability of hitting the point was a finite number, then the probability of hitting the dartsboard would be infinite, because each point has the same probability, and there are an infinite number of points. But we can only have a probability between 0 and 1. If the probability was 0, then the probability of hitting the dartsboard would be 0, which is not true. So what we need is a probability that will times by infinity to give 1. This is called infinitesimal. Infinitesimal is smaller than every number and is infinitely small. We can use infinitesimal to find the area of a circle, as Dr. James Grime explains here.
But people use them to solve problems like this. So let's say I have a circle and I want to know the area. So this is one way you could do it. I could take my circle and I could split it up into triangles. These are meant to be very small, thin triangles. These are wedges at the moment, but that's the problem. We're going to pretend they are triangles. Now, they are wedges. If I pretend it's a triangle, that means it has a straight base. But the thinner it is, then the closer it would be to a triangle. So you kind of say, OK, well, let's pretend they're really, really slim. Like the base is an infinitesimal, really slim, as slim as possible. And then what you do is you take this circle of triangles and you kind of unwrap it like a hand fan. You know, when you take a hand fan, you go like that. So that's what I'll do with this circle. That's my first triangle down here, right? So that's my centre. I'll take my first triangle, right? So there it is, down here at the bottom. I take the second triangle, still connected to the centre. I've kind of stretched it though, so it looks like that. And I take the next triangle, it's a bit stretched again. It looks like that. And I take the next triangle. Right, so I take all my triangles, I stretch them out. They're all connected to the centre though, like they were before. Right, so they get really stretched out, really thin. So they turn to this, right? It's actually turned it into a triangle. You can see that? Can you see that triangle I've done? My drawing is bad. You see, that's a triangle. Now, each of these triangles here, the slim triangles, have the same area as they did to begin with. They've been stretched. The perimeter is different, but they have the same area. Because what is the area of a triangle? It's a half the base times the height. Although they've been stretched, they've got the same height up to here. They've got the same base, and so the area is the same. But the big triangle I've made, it has height altogether, the radius of the circle, r. And the length of its base is the circumference of the circle. So what is the area of this triangle? It is a half. The base is the circumference, the height is the radius. That's the area of the triangle. The circumference, 2 pi r, right? So it's a half times 2 pi r for the circumference times r. And you get pi r squared, and that is the area of the circle. You get the right formula for the area of the circle. And so you did it by splitting it up into thin bits and kind of adding them together with this clever idea.
Infinitesimals can also explain change, and they are used in calculus, which is basically the maths of change. If we want to find the area under a curve, we can split that area into rectangles, which you know the area of, like this. The smaller the width of the rectangles, the more accurate the area is. If the rectangles had an infinitesimal width, they would take up the whole area under the curve, and so we would have the area of the curve. Infinity is used in limits. For example, if we have a sequence like 3x squared plus 4 over 4x squared plus 8, we can work out the limiting value of the sequence, which is the value the sequence sort of ends up at, as x tends to infinity, which basically means as x gets extremely big. What we do is we take each term and divide it by the highest power. In this case, it's x squared. So we get 3 plus 4 over x squared all over 4 plus 8 over x squared. So, as x get bigger, 4 over x squared and 8 over x squared become insignificant. So we ignore these and we get 3 over 4. So the limiting value of the sequence is 3/4, which is 0.75. So the sequence will never get bigger than 0.75. We can also use these limits in physics. For example, what is the fastest a moving object can go? This can be determined by taking the limit as the particle's energy tends to infinity. According to special relativity, the fastest speed which an object can go at is the speed of light. We also use infinity in physics when talking about gravity. Where is gravity pulling us towards? Well, the centre of the Earth. But where is the Earth being pulled towards? The centre of the solar system, which is our Sun. But where is the Sun being pulled towards? The centre of our galaxy. But where's the galaxy being pulled towards? Well, the centre of our universe. The force F is proportional to 1 over the distance squared. This means that the force equals a constant number divided by the distance squared. So, where is the force 0? Well, this is when the constant divided by the distance equals 0, which is when the distance is infinite. So basically, the force of gravity at infinity is 0. However, when we say this, we are ignoring infinitesimals, as we often do in physics. So, as we've seen, infinity and infinitesimals have many uses, but they may have even more in the future. Who knows, if there are an infinite number of universes, there could be another you watching this documentary. Maybe you will be the